Welcome to qnawire.
Today we're looking at the thermal properties of human skin. So this is approximately at a temperature of 34 degrees Celsius, and so this is 311 Kelvin. For part A, we want to find what wavelength of light is emitted the most by a person. So we'll use Wien's law, which says that wavelength is there are many ways of writing this. We can write it as 2.9 million nanometers times a Kelvin divided by the temperature in Kelvin. So this is 2.9 times 10 to the 6th nanometers times a Kelvin divided by 311 Kelvin. And so this comes out to 9,324.76 nanometers. And this is infrared light. Part B asks, how much power would be radiated by a typical person. So we can write that P as using the Stefan-Boltzmann law. It's basically going to be like the surface area of the person times sigma times T to the fourth. So let's use a total area of maybe a third of a square meter. So this is times 5.67 times 10 to the negative 8th watts per square meter per Kelvin to the fourth times 311 Kelvin to the fourth power. And so this should be about 176.8 watts or so. And then if we're looking at the power they absorb from a room, so I assumed that the human skin emits mostly, all the heat that's passing through it. It doesn't really absorb much. So we want to also know how much power is absorbed by a person, not by their skin, but by a person, in which the room temperature is 20 degrees Celsius. So this is 293 Kelvin. So then the power absorbed by this is really going to be the absorption of human skin, which is, basically about 1. So it'll be the same, sigma times T to the fourth times the same area, but our temperature is, of course, different. So we'll have 293 to the fourth times 5.67 times 10 to the negative 8 divided by 3. Write this as maybe 139.29 watts. So you can see you're actually going to have it be a net radiator of energy because you're emitting more power than you're absorbing.